Question 1 from your sample exam. Part A. What does the 92% stand for in a 92% confidence interval of a population mean? Well, the population mean equals mu, right? It's mu. We know that. Well, a confidence interval has a lower limit and an upper limit, right? Such that mu is in between this lower limit and this upper limit. Now, if you have a 92% confidence interval, we say that if you repeatedly calculate a confidence interval, so calculate a confidence interval, then 92% of the cases mu will be in this confidence interval. Right? Does that make sense? Well, yes. Because we calculate a confidence interval for mu, 92% confident. We're 92% confident that mu is gonna be in this interval. So if we keep constructing confidence intervals, then 92% of the cases, so 92% of these intervals will contain mu, right? Well, that's part A. That was rather quick. For part B, what's asked? In a hypothesis test, a p-value of 0.02 means there is only probability of 0.02 that the null hypothesis is correct. Well, is it true or false? I'd suggest you think about it. Well, it's false, of course, right? Because what was the p-value? The p-value is the probability, is the tail probability. And what does that mean? Well, suppose we have some distribution, right? It goes like this, and we observe a t. So we have a t observed from our sample. This is that minus t observed from the sample. So suppose we know that t is x bar minus mu over, not sigma, but s, over s over square root of n, right? Where x bar is the sample mean, mu is your population mean under H0, for example. Then we got s, standard deviation, also from your sample, and n is sample size, right? We know this. So suppose you have some given parameters that x bar is 15, your sample average, then under H0 mu is going to be, let's say, 12. You know the standard deviation is going to be, let's think of something, say 3, and your n is 20, right? So that gives you 3 over square root of 20, which is equal to, let's calculate it real quick, should have done that, 4.47. Okay, so we say that our t observed, this is our t observed from our sample, this is 4.47. Now, due to symmetry, we know we have a symmetric distribution, the t distribution. We know that minus 4.47 is going to be here on the other side, right? So this shaded area here, well, think of it. So the p-value is the tail probability. Tail probability. Should have written that down. Yes. So the p-value is the probability of observing a t more extreme than our t observed, right? So what does that mean? That we want to know the probability of obtaining a t that's more extreme, so here, this way, larger than t observed, but since it's two-sided, right, it's symmetrical also smaller than minus t observed. We want to know this probability, the shaded area. So that's gonna be, let's do it over here, that's gonna be probability of t being larger than t observed, right, that's this, plus the probability of t being smaller than minus t observed, right, that comes from this area. So this area we want to know. Well, we know that's going to be equal to, due to symmetry, which we should not forget, 2 times p, the probability of observing a t larger than the one we already observed. This is going to be equal to, let's not make some confusion here, 2 times probability t larger than, what was it, 4.47, right? And what's that going to be? Well, is 0.02 according to the question. So that's how we answer the question. Well, they say, does it mean that a p-value of 0.02 means that there is only probability of 0.02 that the null hypothesis is correct? No, this is false, of course, because the p-value says we have a sample, and from there we observe some t-score, which was 4.47. Now we want to know the probability that we want to know the probability of obtaining a t as at least as extreme as the one we observed, right? So that's here. But symmetry, it could also be smaller than, right? That's in this two-sided hypothesis test. So in that case, then this will be 0.01, 0.01, add them up, 0.02 is your p-value, right? That makes sense. In the case of a one-sided hypothesis test, you'd have, again, our famous bell-shaped curve. You get a t observed, well, at least as extreme as, so suppose h1 would be mu is larger than some mu. Let's just call the constant a. So suppose we have a one-sided test, then we only care about, in extreme, we only care about larger than, right? And I think you're getting it. But suppose you have that h1 is going to be mu smaller than some constant, then we care about this area, right? And then this will be 0.02, 0.02. Yep, that's it. Well, that's it. It was quite easy. Just think of the definitions and that's all.